guys. So last time you know that we were doing the color of complexes. Okay, and I told you all about the color of complexes, but we have to write down the points for that. Okay, so let's write down the points for the color of complexes. So color of complexes. I'm going to write down all the points, whatever we have done last time. Okay. So one by one, I'm going to write down the point. If you are unable to understand any point because we have discussed the concept last time. So if you are unable to understand any concept, you could ask me, I can repeat it for you. Okay. So the first point, there are five d orbitals out of which the three d orbitals are dxy, dyz. These are the names of the d orbitals, and dzx are present in between the axis, whereas the two d orbitals are present on the axis. So you just write down the names: dx square minus y square and dz square are present on the axis. Okay, so this is the first point. The second point, all five d orbitals are present on the axis. Sorry, are present on the same energy level as transition matter has not formed any compound or complex. Number three, as a ligand approaches the transition metal, for making a complex, it provides its electrons either to the axis in case of octahedral complex, or in between the axis in case of tetrahedral complex. Okay. So in case of octahedral complex the ligand provides its electrons to the axis. So the two d orbitals are present. This is the last time thing we have done. I'm just writing all the previous concept we have done last time. So there is nothing new. So keep remember that. Okay. So the two d orbitals present on the axis experience greater repulsion. So what we were doing, so the two d orbitals present on the axis experience greater repulsion as compared to d orbitals present in between the axis. Okay. The next point, the two d orbitals will shift slightly at high energy level as compared to the three d orbitals in between the axis. Okay. So I told you that the 5d orbitals, okay, they would split up into two sets. Uh, the two d orbitals which are present on the axis, they experience greater repulsion. So they will shift slightly at high energy level, and three d orbitals would remain at low energy level. In case of octahedral complex, we are just considering octa. In tetrahedral complex, this is reverse because the electrons they are donated by the ligand in between the axis. So three d orbitals experience greater repulsion, so they would shift slightly at high energy level, and two would remain at low energy level. So two d orbitals will shift slightly at high energy level, uh, whereas the three d orbitals would remain at low energy level. So D subshell splits up into two sets of d orbitals, two at high energy level and three at low energy level. Okay. the difference of energy between two sets of d orbitals is delta E and comes in the range of visible light. Number 8, visible light is able to cause D that E transition. D dash E transition means jumping of electron from low energy d orbital to high energy d orbital. So due to absorbance of visible light, different color complexes are formed. Okay, so this is the reason, my dear, why the transition elements they form the colored complexes. Okay, copper in it is attached with the chloride CuCl4 minus 2. It form the yellow complex. Okay, whereas copper with water it form the blue complex. So, why this is the difference? Because the ligand repulsive forces they would shift the d orbitals at different energy levels. Okay, due to difference in energy levels, different absorbance of light would take place. One more thing we should write up here: the delta E depends on the type and strength of ligand. Okay, so this is the final point. And okay, my dear students, now we are going to start with the last part of this chapter. That is the types of complexes and isomerism. Okay, in them. So let's start with the types of complexes and isomerism. So let's start, my dear students, with the types of complexes and isomerism in them. So the first thing up here, there are three types of the complexes. The first one that is called as the linear complex. In the linear complex, the two dative bonds they are present. Two dative bonds with the central metal ion. Okay. The second one that is the tetrahedral complex. And the third one that is the square barrel complex. So these two things they are having the four dative bond with central metal ions. Number 4, my dear, that is the octahedral complex. So it forms 6 dative bonds. Okay. Now, one by one, we are going to discuss them and have a look that which type of the isomerism they would exhibit. Okay. First of all, for transition metal, I'm going to use the word T for it, or M. M would be enough. M for metal. Okay. So when I'm going to write the word M, M means it's a transition metal ion. Okay. So now, first of all, linear complex. Now, linear complex, how is it that silver ion, okay, it form a linear complex with the 2 ammonia molecules. Ammonia forms 2 dative bonds. The 2 ammonia molecules form 2 dative bonds with it, like that. Okay, and the charge on the silver, it would come on whole of this thing because ammonia, that is neutral. If you want to write it in a simple way, so Ag NH3 twice, and this is having the positive 1 charge on it. Okay, like that. So if you look, this is having the 2 dative bond and its angle, that is 180 degree, and the shape, that is radial. Did you get it? Yes. Okay, the second thing, my dear, that is the tetrahedral complex. Tetrahedral complex, I told you, they have got 4 dative bonds. Okay, so you got 4 dative bonds. Let's suppose this is metal M, and the ligands I'm going to take, that is A, B, C, and D. So this A, B, C, and D, all of these are 4 different monodentate ligands. Okay. So M for metal, this is the metal, and these A, B, C, D, all of them, they are 4 different monodentate ligands. Monodentate means can form 1 dative bond. So tetrahedral complex, my dear, they have got the shape like that. T, one line is up here, one is up here, one is the dotted line like that, and one is the triangle. So this is A, this is B, this is C, and this is D. Okay, M लिख दो यार, T लिख दो यार, जरा उससे T लिख दे यार, ट्रांजिशन मेटल की जगह इधर मैंने कहा था ये T लिख दो यार, ट्रांजिशन मेटल है ना, T लिख दें ज्यादा बेहतर है. Okay, so these tetrahedral complex, they can form the isomerism when all the 4 are monodentate ligands and they are all different. Then they can form the isomerism. And what type of isomerism they do exhibit? You know that this one would show this optical isomerism like that. T, one line is up here. This triangle would come on that side. This is dotted line, and this is a straight line. So this is A. Here it would become B, this one would be C, and this one would be B. So this is the mirror. So both of them, they are mirror image. So they are called as the optical isomers. Optical isomers, and they are also called as the enantiomers. Okay, so you can use any of the word for it. Okay, so these two are the tetrahedral complex can only form isomerism when it has the four different ligands, four different monodentate ligands. Okay, so then it can form. Then it can form the optical isomerism. If it gets the two ligands same ligands monodentate, so it cannot form the isomerism. Keep remember that. So tetrahedral complexes can show optical isomerism only when all the four ligands are monodentate and different. Okay, तो सारे डिफरेंट जी सारे डिफरेंट हों तब होंगे ठीक है इसमें अगर कोई सेम आ गया तो तब आपकी नहीं होगी दैट्स द थिंग आई एम सेइंग okay guys now the third one we are going to discuss that is the square planar the shape of square planar that is different but it is also having the four dating points. Okay. Okay, my dear students, now have a look at the first option. This is T, A2 and B2. Okay, so A and B, they both are monodentate ligands, two different. Okay, now the shape of the square planar is like that. This is the T. Here we should put the dotted line, and here we should put the triangle like that. Okay, now this is A and A. This is B and B. Okay, so if you look, this A and A, they are going to face each other. B and B, they are going to face each other. So this is this. And if you want to make the trans of it, so it would be like that. This is A, this is A. This is B, this is B. So if you look from that side or even that side, the different groups are present. So the same groups are present diagonally to each other. So this is called as the Sussex trans. Okay, this is the first option. The second option for square planar, P, A to B. So A, that is the monodentate ligand, whereas B, that is bidentate ligand. Okay, so if you see, this is T, make like that, and this one make like that. So the bidentate ligand I'm going to take up here, that is I told you earlier, ethyl 1,2-diamine, CH2, this is NH2, and this is NH2. So the skeletal formula of this one would be, these are the two carbons. So this is the skeletal formula, these are the two corners. The corners contain carbon and hydrogen, and here we write only nitrogen. So this one shows the bidentate ligand. Okay, so if you look up here, nitrogen, this is nitrogen. Okay, and this is A and A. So in this one, we got only one bidentate ligand. Okay, guys. So this one did not show any isomerism because this is having only one bidentate ligand, so does not show any cis trans. Okay, and this one, the same things are present up here, and this is a different thing, so it does not show the optical isomerism. So this one just does not show any isomerism, no isomerism in that case. Okay. So we will continue, guys, inshallah ta'ala, next time. So tomorrow our chapter, this chapter would be finished, and then we will start with the group 2. So group 2 would be finished in one day. Okay. So we will finish this whole inorganic chemistry, inshallah ta'ala, in this week, and we will start with the analytical chemistry after that.